In today's lecture, we are going to look at how we can use polar coordinates in the realm of double integrals. You can think of this as a change of variable or a change of coordinates. When you did single integrals, you may have made a substitution, a change of variable to simplify the integral. And essentially this is what we're going to look at today, but in the environment of double integrals. So the idea is you've got some difficult integral over some, difficult set or a region. How can you simplify the description of that region and hence the actual integral itself? So we're going to be working with polar coordinates today. So just to remind ourselves, so I've got a point P in the xy plane. In polar coordinates, my variables are an angle to the positive OX axis and some distance r to the origin. Now, in particular, for our study today, these polar coordinates are going to be useful for describing curved regions. We sometimes refer to them as sort of angular sectors or polar rectangles. So an example of a polar rectangle is just this pink region here. Now you may look at it and go, hang on, it doesn't look like a rectangle. Can anyone tell me why this is actually might be considered a rectangle? Well, one reason is that if I want to describe this region in terms of our variables r and theta, you can see theta to cover this region. Theta goes from some number theta 1 up to theta 2. Theta 1 and theta 2 are just constants. And the same if I go out to r. So say from here to here, that distance is, say, r1. And from here to here, that distance is r2. They're constants. Now, if you think how you describe a rectangle in the xy plane, you use, say, x between a constant a and a constant b, y between a constant c and a constant d. So it's very similar. Very similar. Okay, so just to recall, remember that the relationship between Cartesian coordinates and these polar coordinates is just given here. And if I've got, say, a function of two variables, x and y, then I can replace x and y with these change of variables or change of coordinates with, respectively, r cos theta and r sine theta. Now, this is important. The following change of variables formula for some polar rectangle. So imagine this is the region of integration, and sort of this distance is r1, this distance is r2. Then the double integral of f over that polar rectangle r is just the following iterated integral. As you can see, I've replaced x with r cosine theta, y with r sine theta, and here's the important part. I've replaced dA, known as the area element, with r d theta. Now, this is very important. The extra factor of r in the integrand on the right-hand side. you're multiplying f by that little r. So how does that? I mean, this is just an iterated integral, so it's no problem to evaluate. You just do the inside integral first, and then move on to the outside integral. But you've got that extra factor of r there. Where does that come from? Ah, well, I'm glad you asked. Okay. Well, before we get to that, and actually, I'm going to show that as a special case of the following. Okay, so just suppose I've got a function of r and theta. It doesn't have to be, this function here, but just a general function. I'm going to claim that the integral of g over my polar rectangle is just the following. So where does that come from? Well, again, you can set up your Riemann sums. All I'm going to do is basically slice up this region in the following way. I'm going to use cuts like this. Okay? So I'm going to cut it like that, and I'll get some tiny little polar rectangle inside. Think of that little polar rectangle as this. Now, you can form this wedge, so the wedge, if that's my little rectangle, the wedge would be going all the way down to the origin. I can form this wedge. Let's say that orangey wedge has area, say, delta A. Now, let's try to calculate the area of that little polar rectangle. It's claimed that the area is just r, delta theta, where r is chosen in here to be, I guess, it's you're sort of averaging the radii for this sort of large sector and this smaller blue sector. And you sort of choose r in there as the average. You don't have to do that, we're just doing that for convenience. Now, if I've got a sector with, say, sort of sector from, say, a disk or something, or a circle, with radius L, the area of this is just a half L squared theta. Now, we can calculate the area of this little orange polar rectangle by taking the area of the big sector and minusing the area of the small sector. Okay, so that's exactly what we've done down here. So the area of the big sector is going to be something like this. Well, from here to here, it's r plus delta r on 2 all squared times the sort of angle delta theta minus the area of the small sector. Now if you expand this out and simplify, and of course you can cancel, so I'm going to get something like this. Okay. Well, let's consider our Riemann sums So imagine that's my sample point, say P sub ij. This is my Riemann sum. And then I can replace delta A with this. And then take the limit. This is going to go to something like this by, you can show that this is true using Fubini's theorem. And I've got that extra factor of R. Okay, so that's a little, again, I haven't been super rigorous there. I've just want to give you a flavour for why it's true. People always ask, where does that factor of R come from? Why is it there? Well, now you have some idea of where it comes from. Okay. Let's do some problems though. Sorry, before we get to that, how does this relate back to this formula back here? Well, let me just squeeze it in. If G of R theta equals F of R cos theta R sine theta, then we have our change of variables. Okay, what we're most concentrating on though is of course trying to do the problems and really understanding we want you to be able to solve the problems associated with this. So that's really what I'm going to concentrate on. Okay, now just to refresh everyone's memory, there's really two parts to these double integrals. Number one, you want to mathematically describe the region of integration using some sort of inequalities. And secondly, you actually want to do the integration. So here we've got describe in polar coordinates the set of points of the unit disk omega, and that disk has its centre at the origin, and the points of interest lie in the first quadrant. So let's just draw in the first quadrant. Our region of integration is going to be here. So let's describe it. Well, how do you describe these things in terms of polar coordinates? Well, again, in the previous lectures I was drawing vertical lines and horizontal lines, and I was looking at where those lines entered the region and where they left the region. With polars, start at the origin and draw a line going outward. Where does this line enter our region? It enters it at r equals 0, and it exits at r equals 1. Now, how much of a rotation do I need to cover my area? Between 0 and pi on 2. Okay, so one way of doing this, of course you can remember it in your own way, is to draw that little line. Where does that line enter the region? Where does that line leave the region? They're the bounds on your R. The second part is, if I need to rotate, how much of a rotation do I need to do to cover the area? Okay, so our integral, so let's make we'll make the change of variables in a second. Okay, so we're going to have this. Now we replace x with r cos theta. We replace y with r sine theta. And replace dA with r dr d theta. Don't forget that factor of r on the end. That's one of the biggest mistakes or oversights that students make. They get everything else right, they forget the factor of r. even if they write it down, sometimes they forget it's there. Okay, you've got to remember we're multiplying this r with all of this. Okay, that's probably the most common mistake with these problems. So I can use cos squared plus sine squared equals 1. I can take the absolute value. R is positive here anyway, so there's no worries about that. So I'm going to get that with an r. So I'm going to get r squared dr d theta. Okay, so I do the inside integral first. If I integrate that with respect to r, I'm going to get 1/3 r cubed, and at 1 I'll just get the following. And so if I integrate that again, I'll just get 1/3 times pi on 2. Okay? Not very difficult, right? Make a change of coordinates. Replace dA with r dr d theta. Do the integral. Okay? Now, how would I interpret that answer? Just, if I wanted to interpret that answer, well, if I cover this up, what's the surface associated with this function? Root x squared plus y squared. What's the surface? What kind of surface is it? Cone. It's a cone, right? So if I wanted to put some sort of, a slight bit of meaning into it, you've got this cone, and this little region here is just going to be this sort of part there. So the actual value, pi on 6, is just the volume above that shaded area in the xy plane and below the cone. Okay? So our answer is just the volume above this little shaded bit in the xy plane, but below the cone. So pretty easy, that one. Notice here, the upper and lower limits of integration are constants. Okay, we're talking about polar rectangles, so these are constants. You can generalize this idea to more general regions. So over here, the order of the dr and d theta, you can swap them and swap the two integral signs and still do the calculations. Fubini's theorem, right? Because we're sort of working again with constants here. Over here, the order is important. Okay, you can't just switch these willy-nilly. Notice in this setup, the thetas are always on the outside. So the theta's here and the d theta here. They should be constants from that setup. Otherwise, you're not going to get a number for your answer. Okay, slightly more challenging problem. Let R be the region that lies inside the cardioid. R equals 1 plus cosine theta, and outside the circle, R's 1. Mathematically describe our region and thus write down the explicit double integral for the area of R. Okay, well, first of all, let's try to draw R. That probably seems like a good idea. So the way I'm going to do that, I'm just going to draw this function in this on this set of axes. Now, essentially, this is just the cosine curve shifted up 1 unit. Okay, so it's not super difficult to draw. Okay, so I'm going to get, whoops. Okay, mine's a little bit shabby. Now, what I would like to do is transfer everything into the xy plane. So in the xy plane, let's draw in the circle r equals 1 first. That's probably the easiest. Okay, there it is. And now I need to somehow draw in the curve over here, Well, the way I usually do these curves, you would have seen them in Math 1131 in first year. You just start here. You know this value's got to lie on the x-axis. The value here has to lie on the positive x-axis, the positive y-axis, this value. This value here has to lie over here somewhere, and you just sort of keep going around. So when theta equals 0, r equals 2. So you'd start out there somewhere. And then you can see as theta increases, r steadily decreases. When theta equals pi on 2, r is just 1. So I would think that this is 1 here. So this is going to come up here like this. And then it keeps getting closer and closer to 0. So let me see if I can draw this in. And then it's just the same on the other side. Cardioid. Looks like a little heart. Oh. Okay, so we want the region that lies inside the cardioid, which is just this curve here, and outside the circle. So our region in this setup would be here. Okay, so now this is important because we want to determine the limits of integration. We know that the area of a region is just the double integral of dA, or a double integral of 1 over the region. Now, I know I've got to replace this, if I go to polars, I've got to replace this dA with r dr d theta. But what about the limits of integration? Okay, well, if I draw this line, it enters the region at r equals 1, and it leaves the region at r equals 1 plus cosine theta. Okay, enters the region at r equals 1, leaves the region at r equals 1 plus cosine theta. So that's that's a pair of the limits of integration. What about theta? What do you think the bounds on theta will be for sweeping out my region R? Anyone? Well, I guess I start down here and I rotate this way and up to here. So theta would be between minus pi on 2 and positive pi on 2. Okay? So you can see that sort of draws on quite a few elements that you've seen in first year. Firstly, sketching the region is non-trivial. And then actually working out the limits of integration, again, that's, it's not straightforward. But it's hard to even write that down if you can't draw the picture. So for these kinds of problems, if you can't draw a picture, well, you're in trouble to start with. So I usually go from here to here and then draw my lines in and try to get the limits of integration. All right. We've got a thin plate with constant density, and it covers this region here. This question asks us to calculate the so-called polar moment of inertia about the origin. Now, we talked about this in the previous lecture, but here we'll use polar coordinates. And this is, in general, a good starting point for calculating these polar moments of inertia. And I'll show you why in a minute. Okay, so let's draw our region. Okay, it's the unit sort of a disk, but just in the first quadrant. So let's call that R. So that's where our plate is located. The polar moment, so let's just put this into polars. So here, R is just our region R. If I wanted to draw something in there like that. Little r is between 0 and pi on 2. Oh, sorry, that's theta. Theta is between 0 and pi on 2, and r is between 0 and 1. Now, polar moment of inertia about the origin. It's just okay, so it's just going to be this. Times delta. So you've got some density. Yes, the density function's in there as well. So this is delta times x squared plus y squared. Okay, now in here delta's a constant, so it's equal to 1. So we're not going to worry about that anyway. Let's put this into our polar form. So delta's just 1. Theta's between 0 and pi on 2. R's between 1 and 0. Now, replace x with r cosine theta, y with r sine theta. And replace dA with r dr d theta. Now, hopefully you can see how the change of coordinates is going to really simplify that. Okay, the x squared plus y squared is pretty much going to simplify massively, and I'm just left with a fairly reasonable integration. So cos squared plus sine squared equals 1. So I'll get r cubed dr d theta. So I want to do the inside integral first. I'm going to get a quarter, and then my final answer should be pi on 8. Okay? Now, if you didn't move to polar coordinates, think about how you would describe your region in Cartesians. You'd have to get the equation for this sort of upper bounding curve. You can get it, it'd be something like y equals positive root squared. And then you'd have to integrate, put that nasty square root sign into your integral and integrate it again. So that's one of the motivations for these new coordinates, these new substitutions. You don't want to be messing around with nasty square root signs in your, or any other nasty things in your integral signs. Okay? I mean, if you want to, you can try to do that without using polar coordinates. Be my guest. Be my guest. But you want to make things easy, not hard. You want to work smarter, not harder. Okay? So how do you know when to make these change of variables, these change of coordinates? Well, one way, at least in my opinion, look at the integrand. Look at the thing you're integrating. If it's an x squared plus y squared, and your regions are suitable, yeah, absolutely you want to make the change of coordinates. Okay, you strongly want to consider making these move to polar coordinates if you've got something like x squared plus y squared in the integrand. Okay? Now, I have talked a little bit about where this factor of r comes from, but I just wanted to give you the bigger picture. There is a bigger picture going on. Okay? It's not just all about polar coordinates. You can think, I guess in this context, what's happening is your region of integration in the xy plane's here. Okay? But in the Cartesian r theta plane, that polar rectangle actually becomes a rectangle. Okay? So what happens is some transformation or some map acts on r and theta, and it maps everything, say in that set G, into the xy plane. You get this image R. Now, let's look at the Jacobian of this matrix on the right. Okay, so you can think of this as the mapping T. Now, let's look at the Jacobian of this matrix here. Okay, if I calculate the partial derivatives, I'll get this. Now, what's the determinant of that matrix, of that Jacobian matrix? Well, it's just that times that minus that times that. The determinant, sometimes we write it like this. In this case, we will. It's just that times that minus that times that. Cos squared plus sine squared equals 1. Okay, so if you look at this, that R is actually there. That's that extra factor. Now, this is true, with appropriate assumptions, this is true in general for any change of coordinates. Okay, it's actually the determinant of the Jacobian. That's that little extra factor in the integrand. Okay? Okay, so in the right-hand side of my start equation, I've got that extra factor of R. So the determinant will appear in general, depending on, of course, what coordinates you're using. It won't always be this R. Okay? So this is just a little glimpse. When I said, when we were working with the Jacobian and its determinant, I said we'll get back to this when you do double integrals. This is just a little glimpse. You'll do a lot more of this later on. Okay, guys. Well, that's all I have for you. So I just wanted to make a few comments before we start crying. So if you haven't done Catai, please, today's the last day. If you haven't done it, if you have done it, thank you very much. I've really enjoyed teaching this class, this session. I've been particularly happy with the exam because essentially you proved that you know everything I wanted you to know. So well done. If you see me around, I'll come up and say hello. Don't diss me. I hate it when students, I'm walking down around uni and people go, they just diss me. They go, I know you. You should say hello. I'm not cool anymore. Anyway, but half of you I will see you in my tutorial, but all the best. Good luck with the exam and see you all later.